I'm back, ready to code. Just need to set something up for my stream. I wanted to implement text to speech because I think that would be pretty cool to have set up so that whatever comments come through, I can hear it directly in my ears. So I'm looking on how to do it right now. And no, it's not what I want to do. Otherwise, I'm working through this course and I'm getting pretty far in it. I'm about 50% complete. And I've already did a little bit of each section before I bought the full course. And I bought it because this teacher, Alvin, is really good at explaining things in detail. And he breaks it down so that I can actually understand it around the first go. Otherwise, it takes me multiple times to learn something watching a video when I watch it on YouTube. If it's just a random video, I have to watch it one day and I have to come back the next day. And then finally, I'll be able, over time, be able to kind of absorb it. But when Alvin explains it, it's almost like the first time around I can really understand it. And the thing that I like that he does is use visuals. And I want to probably create some videos like that, but I need to get either PowerPoint or Keynote because I think that's what he's using to make these animations. Or I was thinking maybe I can use CodePen and Framer Motion and try and code up some of the animations for the solutions of these problems. And I think if I could do that, then maybe it would be a cool side project that I can show employers. Yeah. Another thing that I've been looking into is this site called Great Front End. And so as soon as I'm done with all of the explanation videos here, I'm definitely gonna go into Great Front End because my focus is, or what the jobs that I want are full stack developer jobs using JavaScript and TypeScript. So being able to go through these problems with JavaScript would be probably the best bet for me to get those type of jobs. And with the background implementation that I've learned from Alvin, adding it onto what I've already learned from JavaScript, I think I can do pretty well on these. This was an easy problem. Yeah. So let me look at right now. I am trying to set up this text to speech. So let me see. All right, now let me try and set this up. See if I can find a video. Restream text to speech. Oh, there was an application. That's what it was. And you can do it through the application. I was trying to do it through the website, but this is better. Settings. Is there notifications? There's a bot. There it is. Notifications. Enable text to speech. Okay, I think I just have to have it open. And so whoever types, it could now be relayed to my ears. So that is going to be a cool thing to do. Let me try it out. Hello. No, it didn't work. I don't think it worked. Maybe it did. I also gotta have open, let's open the creator dashboard for Twitch. On Twitch and YouTube right now using Restream. And create a dashboard. Let me change this real quick too. Edit video. Change the thumbnail. Save. Stream manager. All right, let's see if I can hear it.
Vmol. Hello.
Okay. Let's see this here. Okay. Let's see this here. I'm confused. I heard it a second ago, and then now I don't hear it. Or maybe it doesn't do multiple times. So, if you comment the same thing multiple times, I won't say it. Hi.
Vmol. Hi.
Yeah, there you go. Okay, cool. Cool. All right. So, let's look at a problem. Write a function overlap subsequence that takes in two strings as arguments. The function should return the length of the longest overlapping subsequence. A subsequence of characters can be created by deleting any character of the string while maintaining the relative order of characters. So we're writing a function overlap subsequence that takes in two strings as arguments. The function should return the length of the longest overlapping subsequence. I think we're under the section linked list right now. So we're going to be using linked lists to solve this problem. And so we have some test cases where this input would be equal to 3 because dog and dog right here. I think that's what it means. Longest overlapping subsequence. So yeah, DOG and DOG, if you remove the A, is the longest, and you're moving the S here, is the longest overlapping subsequence. Here would be CATS, CATS, you gotta remove the letters in between. Here we have fever. 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 Maybe something in between? No? Yeah, fever for 5. And then here's 11, bespoke in, or and you can't reorder it, you just have to remove letters. So no reordering, just removing letters. Kinfolk. 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 Probably an S. An E. SAE. Something like that. Alright, so I get the gist of what we have to do. Now how can we go about this? And how does linked list relate to this? Am I in the right section? Is this really a linked list question? No. Okay, never mind. I was in the wrong section. So where was that? Oh, that was in dynamic programming. Okay, never mind. Yeah, I'll do that later. But for now, I was right before this yesterday. I was doing this linked list section, so let me start there. And so let's do this one. Add list. Write a function add list that takes in the head of the two linked lists representing a number. The nodes of the linked list contain digits as values. The nodes in the input list are reversed. This means that the least significant digit of the number is the head. The function should return the head of a new linked list representing the sum of the input lists. The output list should have digits. The output list should have digits reversed as well. So you must do this by traversing through the linked list once. Okay. So how are we gonna do this?
Leetcode. Hey at Vimel.
Hello, Leetcode. How are you? I set up text to speech, so all the comments are gonna be verbally voiced. I think that would be easier for me to keep track. Although it might get annoying if it's too long. But we'll test it out. But yeah, so I'm going through these questions on structy, and we're on the linked list section right now. So hold on. Let's see. So we have set up this question. Let's make it look nice. Okay. All right. So I know we're gonna have some nodes. And we're going to represent, let's take one of these test cases. So we have 1, 2, 6 and 4, 5, 3. And it's going to look like this addition right here. So let's take this. So we're going to add 621 with 354. And the way it looks in a reversed order would be 1, to 2, and let's repeat this. To 6. And we're gonna add that to $354, which would be represented in reverse order. And the input is given with 2 heads, head 1 and head 2. As represent head 1 is this one, and head 2 is this one. And so I think what we can do is output it to another list, another linked list, and okay, so this linked list will be the tail. So we're gonna have like a dummy node, right? And I'll set a tail here. And then I had a similar problem where we merge the list. So we'll probably use the same type of system to add them together, similar to how you would merge the list. And so one thing we would do is set pointers. And so let's see, let's copy this. So this is the initial setup. And we're gonna have two pointers, current 1 and current 2. Current 1, current 2, and they both start here. Okay. So let's look at this example. Say we wanted to compute 621 and 354 normally. The sum is 975. So you would add 1 and 4 to get 5, 2 and 5 to get 7, 6 and 3 to get 9. And it would look like 579. It seems pretty easy when you don't have any carryover, because I know eventually when you add, you might have carryover. But without carryover, it seems like you would just loop through both the lists at the same time and just add the two values together. And in this new list, we create a new node that's the sum of these values, right? So that would be the easy case. So maybe we do that. We say 4 plus 1 . So maybe it's like while current 1 and current 2 . So while they're not null, we want to, and before we do that, so this setup right here, we have 2 heads. This setup right here, that's not what I wanted to do, would be like current 1 is equal to head 1, current 2 is equal to head 2, and then we would need to set up a dummy node. So dummy is equal to node 0, and tail is equal to dummy dot next. And that's, wait, no, tail is equal to dummy. right? And then we're going to set tail.next to, we're going to set tail.next to the solutions, right? To the solution, that's how we create the solution list. And then at the end, we're going to return dummy.next, getting rid of the dummy node and just returning the solution list. So when we get to this part right here where we're looping through, now we have a current 1 and a current 2 that we set up previously. And we're again going to loop through to the end. And we can say at each iteration, we want to add the values of current 1 and current 2. And we're going to add them together, and we're going to store the value into the node. It's a new node that we're going to create. We're going to store that value into a new node. And that node is going to be the next value in the tail. So tail.next is going to be equal to this node. Yeah, so tail.next is going to be equal to this node. And to make sure that we move the pointers to the next position, we're going to set the current pointer to the next node in the list. So after we add them, we move the pointers. And again, we're solving this problem before we have to think about the carryover type of example. Well, let's just do it right now without carryover. And I think this would be good for a non-carryover answer at the end again. So we would do this a couple times. And so we start out here, and then next we would move this over. Let's do that. Boom. Current would be here. Current 2 would be here. 1 plus 4 is equal to 5. And so take this arrow, make this a little bit shorter. So the first node we added would be with the value of 5. Maybe let's make this green. Green for solution. And then we do it again. And so 2 plus 5 is 7. And then we put 7 here. And we do it again. this one should be here. Let's move this over right here. Here. We'll do 6. 6 plus 3 is 9. The last one. 6 plus 3 is 9. And 6 plus 3 is 9. And then this will be moved to null. And once it reaches null, now now it ends and we return null. All right. And we gotta add this right here. This would be the answer. And so we would return just this part right here. And that would be the answer. Tail.next. Return tail.next. Or sorry, return dummy.next. Because tail would be more, you would move tail. Tail would be all the way over here or even here. Probably like here. Because when you go here, another thing you have to do, you would set tail.next. You would have to also move tail. So you would also have to move tail every time. So tail would start off here at the top, right? And then tail would be here. And then tail would be here. And then tail would be here. So you don't want to return tail, you want to return, the dummy is still at the top here. You want to return dummy.next. Okay, so this is a simple addition. And so now what do we do if there's carryover? So in this example, we have 7541. Well, this is not carryover example. So this one is if you have an extra node. So if you were to add one more node onto one of the if you were to add one more node onto one of them. So let's think about that. Let's think about it. So if you add one more node, let's change the numbers here. 7541. One, 4, 5, and 1, 1, 4, 5, and then let's add one more. 7. Just move this down a little bit. Boom. So 1, 4, 5, 7. So if we had this and we had 32, it's actually 2. Boom. Boom. 32 would be 2, 3. So what would happen? We would start out with current 1 and current 2. And we would move both of them. And then once one of them gets into a null value, right? One of them is null now. We can check both and we can say if current 2 is null, then we want to say the tail, because what's going to happen is we're going to have a tail again. This thing is going to be right below it, visually representing it. We're going to have a tail with some values, probably, so you can see here, 3 and 7. So we're gonna have a tail with some values, and we have to add the rest of the list. We have to concatenate the rest of the list. So we're just gonna add a 5 and a 7, like here. And so we're going to say tail.next is current ones, or is current 1. So that way we just add the rest of the list. So again here, we're going to say if current 1, if not current 1, so if it's null, we want to tail dot next is equal to current 2, and then we want to do the opposite for current 2. Yeah, so we want to append the opposite side if the other one is longer. So then those statements will do that. Those if statements will do that. Okay, so now that we got that case done, now we have to look at the carryover. And there's 2 types of carryover. So there's going to be one where you're adding on to the next node, and then one where you're adding on to, or you're creating a new node. So let's look at the one where you're adding on to the node. And so when you're adding on to the node, maybe you can say if the sum, so when you're up at this point right here, and you're adding to 2 values, and you're putting into the node, maybe you can say if the sum is 2 digits, do something. the sum is 2 digits, maybe we can do something. How do we do that? How would we do that? So we're going to have an integer value that's 2 digits. Maybe we use like modulo. I think that's how we would do it. Like you divide by 10 and you have the remainder. Or you do modulo 10. So you would say, if modulo 10 or if the number is greater than 10, so if you add the two numbers and the number is greater than 10, then you do the modulo of that number divided by 10. Does that work? Let me see something real quick. Yeah. And so when you have the remainder, for example, 9 plus 7 is 16. You put the modulo number here. And you add the 1 here. So in our current thing, we just have 2 values added together and we put that into the node. What we want to say, if, let's do this. So the sum is equal to current 1 val, current 2 val. And we say if the sum is greater than 10, or greater than or equal to 10. If sum is greater than or equal to 10, we want to do we create 2 nodes? How does that work? How do we carry over to the next one? Do we have like some sort of variable that's called carryover and we add carryover to the current value, and then maybe we say so let's see that. So before we go into the loop, let's create a variable called carryover. set that equal to 0. And we say if sum is greater than or equal to 10, we can set carryover equal to 1. But once we go into the next one, maybe we also have to check if carryover is equal to 1, then we do something. And if carryover, then we add that. Or we don't need to do that. Or maybe we just add carryover. Whatever carryover is, we just add it. For example, in the node here, we just have sum plus carryover. Carryover, one word. No. So we have sum and carryover. So let's say it's not greater than or equal to 10. Carryover is going to be 0. Either way, both ways, you're going to add sum and carryover. However, there's one scenario where, again, current 1 and current 2, where you're, there's going to be one scenario at the end where you have something like this, and you'll have a carryover of 1 that creates a whole new node. So how do we do that? Is that worth thinking about now, or do we do that later? Because I think I have a solution for if you're just adding. Because if you're just adding, this is the solution. Like, let's not indent this. Let's bring this back here. But we say if sum is greater than or equal to 10, we want to say carry over equal to 1. And maybe we always do sum. We always do sum modulo 10, because if it's not a double-digit number, it's just going to return that number. And if it is a double-digit number, it's going to return the remainder. And so either way, we're going to have 1 digit. And then we're going to add over the carryover. So that works. So I think that's the solution for carryover from the previous node. The thing is, we also have to say, if it's not, then we have to reset it back to 0. So else carry over equal to 0. Maybe there's another way to do that, but yeah, basically, if sum is greater than or equal to 10, we want carryover equal to 1, else carryover equal to 0. Or is there a way to do that where like you have the number and instead of getting the maybe you just subtract. Like you have a number minus 10. No. Let's see. There's like how to split double digit number into two integers. So the ones digit you would do modulo, and the other digit you would do. So instead of this, maybe it would just be this. Sum divided by 10. And so if you had like 16, 10, would be 1. And then this would be 6. 6 plus 1. Okay, so you don't even need this part right here. You don't even need that. But now the last part of this would be, what do we do if we're carrying over to a null spot? That's where we might need the carryover, because let's say we exited, or what do we do if we, another thing is, what do we do if, how do we carry over to so we have this example right here. And the way we are dealing with appending the rest of the characters, I don't know how we would add the carryover onto the rest of it. Because we're just appending, like our, what do we have? So let's bring this up here. So let's copy this. So the way we're doing this, after the while loop, we're just appending, because if one of them's null, the while loop ends. And so we just append the rest of the list. However, if we have a carryover, we're going to need to add that, loop through and add that, just like we see in this example. So how do we do that? Maybe it makes more sense now to have that carryover number. And maybe we say maybe we just keep it a Boolean and we say if carryover is true, then we loop through and we say if carryover is true, because at this point right here, outside of the while loop, we say if not current 1. Tail.next is equal to current 2. If not current 2, tail.next is equal to current 1. If not current 1, so probably something in here where I would add 1 to the head of tail.next, or to the value in tail.next, and tail.next.val. Maybe we would say if tail.next.val or maybe we loop through. We're probably going to have some sort of loop in here, I would think. But I've been struggling too much. Let me see.
Hey programmers, Alvin here. Right now I want to go over an approach we can use for this add list problem. So in this problem, we're going to take in 2 linked lists as inputs. What we want to do is interpret both of these linked lists as if they're numbers, but in reverse order. In other words, if I look at my first list, that represents the number 621, and my second list represents the number 354. Notice that I read the digits of these linked lists backwards, right? And every single node represents 1 digit. And logically, what I need to do is basically compute the sum of these 2 numbers. So just using regular math on the right-hand side, 621 plus 354 should be 975. However, what I want my function to do is take in those reverse number linked lists and return another reverse number linked list that represents the sum. So notice that the logical sum is 975. That means you need to return a new linked list with these nodes of 579, just all the digits backwards, right? Similar to how the digits of our input are reversed, the digits of our output also need to be reversed. So at face value, this can definitely seem like a pretty large and overwhelming problem. The key to victory here is to break things down and really notice what operations we do when we just add up numbers on pen and paper. So just looking at the regular math on the right-hand side, if I was adding up these numbers, typically the way we learn math is we add up starting at the least significant digit. So I take the sum of the 1 and 4. That would give me the 5. Same thing. Now I take the sum of 2 and 5, that'll give me 7. And finally, I take the sum of 6 and 3, giving me 9. And now it's actually pretty convenient because we're given our linked lists in reverse order. That means the ones place, or the least significant digit, is going to be at the front of the linked list, which actually corresponds to the order we typically do the computation. There's going to be a lot of different scenarios to consider for this problem, and I think what will help is we build up each of these scenarios step by step. So I think scenario 1, basically the easiest case would be, what if both of our input lists had the same exact length? So in this particular example, both lists have a length of 3, which makes things a little easy. So what I can do is traverse through both of these linked lists simultaneously. And when it comes to the exact details of how you can implement this, you can either do this iteratively or recursively. What I'm going to show you right now is really a generic strategy that you can do using either tool. So I'm going to start with my pointers at 1 and 4. I can simply take the sum of their values. I know I need to create a new node whose value is 5. At that point, I can just traverse both pointers to the next. Now I can take the sum of 2 and 5, giving me 7. And in my output, I just want to make sure that I can make that connection from my previous node of the output to this next node. I'll leave that in the code though. Next iteration, I take the sum of 6 and 3, giving me 9. And that's actually our full output. Another scenario we should consider is what if our linked list contained a different number of nodes? So let's say I had a different example, and I had inputs such that maybe the first list has 4 digits and the second list only has 2 digits. So let's write the regular math on the side. Recall that these digits are reversed, so I'm really asking for 7,541 plus 32. And to perform the math here, what tricks do we use? Well, if I start in the general way, I take my ones place, so I do 1 plus 2, that gives me a digit of 3. Then I move on to the next larger place. 4 plus 3 gives me 7. And if I go further, things get a little rough here. It looks like I only have digits in my first number and I run out of digits in my second number. Logically, we know that a 5 needs to appear in the output, which kind of implicitly means that 0 is at the front of our second number, basically padding any missing digits as a 0. So if I do 5 plus 0, that would give me the output of 5, which is correct. And likewise for the last digit here, 7 plus 0 would give me 7. And so what we can do is basically treat any missing digits as if they're 0, and that would actually give us the correct type of summing mechanic. So now let's perform that logic in our linked list. So I'm going to have my same pointers as before, and for the most part, it's business as usual, right? 1 plus 2 gives me 3. 4 plus 3 gives me 7, and at this point, when I get to my next iteration, I need to pad some zeros for the second number. And what I'm really suggesting here is that we treat the missing digits as if they're 0. I'm not saying that we actually have to create any new nodes with 0. So we just need to make sure we accomplish this logic in our code somehow. But at this point, I can continue my traversal.
All right, let's see from there. So instead of stopping, like we were doing, and adding, what we're going to do is say while current 1 or current 2. So one of them can be true, the other can be false. But when we sum it together, we got to say if we got to say if current 1 is null, then we got to set it to 0. And we got to say if current 2 is null, we set it to 0. And then we add the sum. But before we check, we actually have to. Here's the thing, because like you can't do things like this on a null object, so it changes. So if we loop through, maybe before everything, we have to say if not null before we do everything. Maybe. So if current 1, then we move it to the next. We say if current 2, move it to the next. So we're only moving it if it's not null. Maybe we do the same thing up here. We say if current 1 how do we make this easy? How do we make this easy in Python? Maybe we do current one val is equal to 0, current 2 val is equal to 0, and then we say if current 1, then current 1 val is equal to current dot val. Seems like a lot to write, but maybe that's just what you have to do. And so this would add the padding, right? We're setting the values equal to 1. This we changed to val. We're setting the values equal to 1, or sorry, equal to 0, unless they're not null. Then we add the value, and then we make them the correct values. And we can still do everything the same. We only move a node if it's not null. So if we were to have these zeros now, there's still the problem. Yeah, let's keep watching.
I do 5 plus 0 gives me 5. I do 7 plus 0 gives me 7. And there we have our completed output. So it looks like we're able to handle lists of all different lengths. And there's one glaring mechanic that we're missing. What happens if we need to carry? So let's change the example. Let's say I had these two linked lists as input. If I write the plain old math on the right-hand side, I'm asking for 39 plus 47. When I start summing the ones place, that would do 9 plus 7. And that would actually give me 16, which if you're familiar with some math means I make the digit a 6 and I carry the 1, right? I break down that 16 into a 6 in the digit and a 1 over in the next place. And then when I get to my tens place, the next digit over to the left, I can do the sum of 1 plus 3 plus 4. So not only do I add up my two regular digits, but I also add the carry from my last addition. And this would give me 8. And that logic would actually be pretty easy to code up in the case of our traversal, right? Just use a variable or even some additional argument. So let's say we're stepping through our linked list now. If I do 9 plus 7, I know I need to create a 6 in the digit, and I carry a 1 over to the next traversal. And at this point, I can move to the next traversal. I do 3 plus 4 plus 1, giving me 8. And at this point, I hit the end of my linked list, and so this is my final answer of 6 to 8, which represents the number 86. Awesome, so that's a basic carry mechanic. And I actually do believe there's one more edge case we might want to think about. What if we need to handle a final carry? What does that mean? So let's take a look at an example like this. So I'm doing 999 plus 6. Let's also take a look at the grade school math on the right-hand side. This is an important scenario to consider because we know that the output is actually going to be longer than either of our input numbers. In other words, let's say I started summing things up here. If I add up the ones place, I do 9 plus 6, which is 15. That means I put a 5 in the digit, and I carry a 1. So I put the 5 over here and carry the 1. At this point, I can do my same like 0 substitution for missing digits. Just do 1 plus 9, which is 10. So I put 0 in the digit and carry another 1. And same thing as before, I do 1 plus 9 is 10. I put 0 in the digit and carry the 1. But since I've hit the end of my numbers, I just put the 1, 0. Notice that the longer of my two inputs was 3 digits long, but because I had a final carry here, my output was actually 4 digits. So how do we reason that behavior out in our traversal? So looking at our linked list, let's say we're stepping through this. If I do 9 plus 6, that's 15, so I put the 5 in the digit and I carry the 1 over to the next frame. Then I can substitute a 0 after the 6. I do 9 plus 1, which is 10, put a 0 in the digit, carry another 1. Do another substitution for my 6 side. And then here, like before, I do 9 plus 1, which is 10, put a 0 in the digit, and I think I should still carry a 1 over to the next frame. And what I can do at this point is actually substitute both of these linked lists as having a 0 after them. Then I can just do 1 plus 0 plus 0, giving me a 1. And that would represent the correct linked list sum. And so it looks like we're going to need some logic to make sure that we stop traversing and stop substituting zeros once both of our linked lists hit their tail, and also my carry is 0. And I'll consider that a check mark for handle final carry. Awesome. So I do believe that these are all the steps we'll need to solve this one. Let's take a look at what the complexity of this general algorithm would be. So if we say that n is the length of list 1 and m is the length of list 2, it seems to be that the time complexity would be the maximum between those two lengths, right? So the max between n and m. And here's the reason why. I know that if one of my lists is longer than the other, then technically I need to iterate really through the longer list, while the other list just has some zeros that are substituted into it. So it's really the longer of my two linked lists. In terms of the space complexity, I would have to use up space to, of course, create the resulting linked list. I have to create new nodes, which, like we said, is going to be roughly the max size between our two linked lists. Just like we saw in the last example, in the worst case, it's going to be 1 greater than the longer of the two lists. But we can drop that plus 1 over there. Notice that if we implement our traversal with either a recursive or iterative strategy, you would actually still end up with the same time and space complexity because we have to generate new nodes in our output. All right, so what I want you to do is try to code up this algorithm on your own. If you get stuck, you can find me in the walkthrough video where I'll show you how to implement this both recursively and iteratively. I'll see you there.
All right, so yeah, I thought of that, like maybe instead of looping, only until, well, one of them are null. Now we maybe choose another loop condition, and we say we stop looping if they're null, if both of them are null and there's no carryover. Maybe that's this doesn't make sense. I don't know why I did this. So if either of them are not null, so both of them are null, but there's a carryover, or carryover. Carryover is equal to 0. So carryover is equal to 0. We want to sum them up, and then we say if carryover is equal to 1, if sum is greater than or equal to 10. Carry over is equal to 1. Sum is greater than or equal to 10. Or you just, instead of doing that, you just go, you add the sum, and then you say carryover, you set carryover, which is equal to sum integer division 10. And so that's going to either be 0 or 1. It's either going to be 0 or 1. And then now, when you're adding the next tail, that's when you do if carryover or yeah. That's when you do plus. So you're going to do the node is equal to current 1 val plus current 2 val plus carryover. So you don't have to do any if statements. It's already a lot of if statements. But you don't need this anymore. And this would be the setup. And then you would just return you would do return dummy next, like here, small. I think this would be the code, maybe. Let's try it. Current 1 is equal to head 1. Current 2 is equal to head 2. Dummy is equal to node 0. And tail is equal to dummy. Carryover is equal to 0. We say while current 1 or current 2 or carryover, we're going to set current 1 val equal to 0, 0. Current 1 and current 2 val is equal to 0. And we're going to say if current 1 maybe we can make it more concise. If current 1, then we want to set current 1 val equal to current 1 dot val, right? We can also at the same time we're done using the value, so we can shift it over. So that way we don't have to repeat the statement. So current 1 is equal to current 1 dot next. And so let's do the same thing for current 2. Okay. So now that we have both values, we want to sum both of them. Current 1 and current 2. We want to find the carryover, which is going to be the sum integer division 10, so it's either going to be 1 or 0. Then we want to set the next tail equal to the node, to a node with the value being current 1 val plus current 2 val plus the carryover. And now we want to shift the pointer if they are valid. Current 1, if current 1, we shift it. Dot next. We do the same thing here. If current 2, we shift it. And then we also need to shift the tail to the next spot, because we just added that new tail. So we need to shift it to that node. And then after we exit the while loop,
Leetcode. You already did that.
I already did which? Oh, I did that. Oh yeah. What a yeah, you're right. I already did that. I forgot that I did that earlier to make it more concise. And okay, so we passed some tests. Thank you, Leetcode. And so we have one here. 17 and 7. I'm doing something wrong. So let's look at that test real quick.
Leetcode. There's a small bug.
Small bug. Small bug. Where is it? Where's the small bug? Turn to... Well, what's happening? We're expecting 6 and 8. We're on this test case, and we're expecting 86. And instead, we're getting this node with 2, with a 1 and a 7. When it should just be 7 in this spot. So what's happening? Let's loop through. So we have
Leetcode. Some should include the carry as well.
some should include the carry. Oh. Some should include the carry. Yeah. Duh. But it should include the carry. Because when you come on to the next round, you just want to add it in. and then you get another carryover. You could get another carryover. What else am I doing wrong though? So what is this 1 and 7? How am I getting that?
Leetcode. You only want to set the least significant digit of sum to the node val.
We want to set the least significant. Digit of sum. Do I do this?
Leetcode. Also, you can't reuse carry underscore over after changing it.
Can't reuse carry over after changing it. Yeah.
Leetcode. Yes, that's right.
I got it. Woo! Thank you. Yeah, so I had to, my
Leetcode.
flaw was, again,
LGTM.
adding the carryover first into the sum. I was just doing it directly into the node value. However, in the node value, what I'm trying to do is get the least significant digit, like you were saying. So yeah. What does LGTM mean? LGTM. Okay, nice. Let's see if they did it.
Hey programmers, Alan here. Right now I want to go over a Python solution for this add list problem. So hopefully you watch the approach video because we're going to implement that strategy. And I think we'll start with it in a recursive version. I'll be sure to show you the iterative version as well at the end. So let me just start by writing some baseline code that will handle at least the easiest case for this problem, right? That's typically when both of my input lists are going to be of the same length and there's no carry required. So what I can do is just write a recursive traversal. So I can stop if my head is none and head 2 is none. So remember I have two linked lists here, right? So if head 1 is none and head 2 is none, then I'm done. And I want to return, basically the linked list represents that sum. If I'm just adding to empty linked lists, then the result should also be empty. So I return none as well. Nice. And now in the recursive case, I actually have 2 nodes, and I need to actually compute their sum. So what I can do is, for each of those nodes, I'm going to look into their values, right? So I'm going to check, right, what's head1.val and also head2.val. And I know those are going to be numbers representing digits of my two linked lists. If I just add them up, that should give me their sum. And for now, I'm considering that there is no carry required. So I'm going to assume that this sum, this quantity, is going to be a single digit for now. And I'll call it just digit. And whatever that digit is, I must create a new node containing that digit. So I can create that node, and I'll pass along that digit as the value into the initialize. And I'll save that as maybe the result. So that's a resulting node. Cool. So at this point, I've just added 2 digits of my input list. Now I need to find the sum of the remaining digits, right? So I'm going to call recursively. I'm going to say add list of head1.next and head2.next, right? So I'm traversing through both. I know that this call is going to give back the head of a linked list, right? That represents the sum. And so whatever I get back there, I'm going to set as results next. So result.next equals whatever node I get back from the sum of the rest. And to complete my recursion, I need every call to return the node it creates. So simply return result, right? Maybe to be clear, I'll call this my result node. So let's test this out. This should at least pass a simple test case. It's passing 0, 0. Like we said, 0, 0 is the case where I have 2 input lists that are the same length and no carry is required. Now let's start adding some more logic into it. So it looks like the next case that we're failing is when we have different lengths. So we're going to need to handle that. So if I make it past this base case, and I know that one of my heads is none, whichever head is none, I want to substitute that value for a 0. So here's what I can do. Because I need to protect myself from doing this line, right? Let's say head 1 is none. You can't say none.val. So instead, what I'll do is maybe create some val variables. I'll say val1, and I'll just use some Python ternary here. I'll say val1 in the scenario where, let's say, head 1 is none, I'm going to substitute that as 0. So 0 if head 1 is none. Otherwise, it's not none, so then actually use head1.val. So just some Python ternary. Again, what is this code doing? When
Okay.
head 1 is none, I'm assigning val1 to 0. Otherwise, I'm just using the head's value as val1.
I can use
And it's
that
going to be
ternary
symmetric
too.
for the right-hand side. So all about val2, head2. And then when I do the addition to calculate the digit, I'm just going to do my val1, val2. So that lets me substitute.
Let me practice that. So, instead of saying can you do multiple things in the else? In that ternary? It's like combined it, it's not really.
Zeros if the digit does not exist. In other words, if the digit is null, or none rather, so val2 over here. So that's looking a little closer. And if I actually ran this code, I would still get an error, probably because of this call, right? What we're trying to fix is the scenario where, let's say, head 1 is none. So now I can make it past this code, and I can compute my next node. But then if head 1 is none, I can't say none.next on this recursive call. So this would error out still. What I need to do is only go on to the next node if it actually exists, right? So maybe what I'll check is some variables again, just very similar pattern to this. So I'll create next one over here. And let's say if head 1 is already none, then just still set it to none. But if it's not none, then what you can do is set it to head 1.next. And so what this is saying is only take a step on the list 1 pointer if you're at a node. If you're at none, then that's okay, just stay at none. That way I can continue to substitute zeros there. And it's just going to be symmetric for 2. And of course, now I can generalize my line 19 and pass along next 1 and next 2. So next 1 and next 2. And I think that will satisfy the second test case. Let's give that a run. So I hopefully can handle some differing length lists. Nice. Getting past 0, 1. So we pass 0, 1. Awesome. And 0, 2 would be about a carry. So I need to work in my carry logic, right? Looking at this math over here, I carry 9 plus 7, right? 9 plus 7 is 16, so 6, and then 1 over here. Looking at my incorrect output, you can see what happened here, right? When I took the sum of those two digits, I actually put a 16 in a node, which is a bad idea. Instead, I want to just put the 6 and carry the 1 over to the next call. So to me, it's about fixing this line then, right? Sometimes this quantity would be over 9, be bigger than 9. If it's bigger than 9, then it's a double-digit number. So maybe a more appropriate name for this would be like sum, right? Because that sum could be over 9, right? It could be a double digit. And if I want to actually get my digit, I know what I can do, I think, is just take the sum, and you can just mod it by 10. If I do a quick sanity check, let's say that my sum was 5, right? If I do 5 mod 10, the result is 5, so digit is 5, and that's good to go. But let's say my sum was a double digit number, like 12. If I do 12 mod 10, I get 2, which would be the correct thing I want to put in the digit. Nice, so this should give me my proper digit. And I also want to code up some carry logic now. So after I compute the sum, I think I'll just kind of use another ternary here. I'll say maybe next carry. So I'm going to generate my next carry. And let's say if my sum is double digit, so if it's bigger than 9, then I should carry over a 1 into the next frame, right? Otherwise, it's a single digit, so I can just carry over 0 in the next frame. Basically, don't carry at all. And if I want to pass that information along, then my recursive call needs to know how much it should additionally add. So I'll pass along the next carry here, right? Next carry is either going to be 1 or 0. There's no possible other carries to have here. Nice, so now that I'm changing this call and how I pass, I want to change this signature. So I want to make this an optional argument so I can still pass these cases here. And I'll say carry by default equals 0. So at the start, we don't need to carry. So that's looking good. And then one thing I need to be sure to do is imagine that we made the recursive call and next carry was 1. Well, according to this code, that stack frame would receive it as this carry variable. We're not really doing anything with this carry variable. What I want to do is now include that carry into my next sum over here. So I should add carry. So that's looking pretty good. Let's go ahead and test that now. That should be our basic carry mechanic. Cool, so we made it a little farther. Looks like we're failing on 0, 3, which is probably another special case over here. Yeah, it looks like test 0, 3 has to do with the final carry, right? So we carry at the very end, causing this 1 over here, right? Because 7 plus 9 gives me 16, carry the 1. 1 plus 8 is 9, plus 4 is 13. I need to have a 1 at the front, which of course means it appears at the end of my linked list. Reverse output there. All right, and so if I need the ability to add any kind of like leftover digits, especially due to a carry, then I need to fix the base case here. Because what this base case says is, hey, as soon as your head 1 and head 2 point to none, in other words, as soon as you're done with your digits, just end your algorithm, return none. But what if I have head 1 is none and head 2 is none, but I still have a carry? So I want to be more specific here. So I want to say, all right, stop if head 1 is none and head 2 is none, and my carry must be 0. If it's not 0, then keep computing, right? Let's say we're doing a final carry. That means that head 1 is none, head 2 is none, but carry is 1, right? So I substitute 0 for both of my values, then I do 0 plus the carry of 1. That would actually create the digit of 1 in my output. So that seems like a good fix. Cool, so let's give it a run. And that should be able to do the final carry for us. Awesome. And there's a nice recursive solution for this add list problem. So it's going to be
Nice.
basically a linear time, really the max between your two linked list lengths, and also a linear for the same reason for your space. Because I'm doing this iteratively, I can just reassign the carry variable now that I used it, put in none here. And then pattern we've seen that should give you that full chain of everything afterwards as well. One thing we need to add in before we test it is, of course, to actually do the traversal for our current 1 and current 2, right? At no point are we setting current 1 to its next. Likewise for current 2. So I think I can do that at the very end, doesn't really matter too much. And so what I want to do is set current 1 equal to current 1 dot next. Likewise for my 2. But what we have to bear in mind is on some iterations, basically when one of your lists is shorter than the other, one of your currents will contain a node, the other current will point to none. And let's say current 1 pointed to none, I can't say none dot next. Right? So I'm going to need similar conditional logic to what I did over here, right? Only traversing to your next node if it's appropriate. So that's pretty easy to do in my iterative code. I can just check. All right, if current 1, if it is...
Yeah, so pretty much did the same. Okay. Okay. So, see this quiz that he has here. What term is commonly used to describe the first node of a linked list, the head? What term is commonly used to describe the last node of a linked list, tail? What is the dummy head pattern for linked lists? You initiate a node with the value of 0, and then you set the tail to that dummy head, and then through each iteration you set tail dot next to create a new linked list, and then you return the dummy dot next to get the head of that linked list. Dummy head pattern is where we use a fake node to act as the head of the linked list. The dummy node is used to simplify edge cases such as inserting the first node into an empty linked list. Okay. The dummy node is used to simplify edge cases such as inserting the first node into an empty linked list. It's where we use a fake node to act as the head of the linked list. What is the optimal complexity we can achieve for searching for a target value in a standard singly linked list? Searching for a target value would be O of n. Searching is O of n. O of n and O1 space we do iteratively. O of n recursive, yeah. What two properties are typically stored in the nodes of a singly linked list? Next and val. Why might the expression current.next.val be unsafe? Because let's say you get to the end. Let's say you're setting while to end when current is null. If you have current.next.val, then you could be at the end of the list where current is not null, but the next value is null. So you would fail because that null value can't have a value property on it. If current is the tail node, the expression throws an error because current.next is null and null property doesn't have a val property. Nice. That's what I said. Awesome. Let's see what he says.
All right, programmers, so that was our run through some linked list problems. We utilize time and time again the traversal algorithm, which could be implemented recursively as well as iteratively. We're going to have more opportunity to practice linked list problems later on in the course, but I think for now it's more important to switch a topic. That way we can do some deep recall later on.
So let's go to this one. Tree pathfinder. Write a function pathfinder that takes in the root of a binary tree and a target value. The function should return an array representing a path to the target value. If the target value is not found in the tree, then return none. You may assume that the tree contains unique values. Root and a target, and you gotta find. You return an array representing a path to the target value. And if it's not found, return none. So we just traverse the tree. And append the values to a list. So we can do depth first search or breadth first search. And I guess we can just start iterative. And depth first search, which would be a stack. And then we could have a resulting array. And we can say, okay, the first thing we got to do is we got to add the root. So if root, then we want to append
Steve Josh.
the roots.
Hello.
Hello, Josh. How you doing? I'm just going through these structy problems. This is like a data structures and algorithms course. And so I'm learning all of these key concepts so that I can do Leetcode problems easier. And right now this one is a
Steve Josh.
binary tree problem.
Nice.
Yeah. I added text to speech too, so that all the comments can be voiced. All right, so we add the root to the stack, then we're gonna loop through while there is a node in the stack. And
Steve Josh. Nice. Your voice is significantly lower than the AI voice.
Let me see. Is the voice really loud? Or here, let me raise my voice. Hello, hello. And then we lower the voice of the AI. Thank you for telling me that. I was gonna, it does sound loud in my ear, but. Let's see, sounds.
Steve Josh. That's better, thanks.
Yeah, let me lower this too. Let me type something.
Vmol. You're welcome.
Alright, I lowered the voice too. Let me see now. Hello, hello, testing. Let me see now.
Vmol.
Hello, hello, testing.
Testing.
Let me see now.
Vmol.
Hello, hello, testing.
Testing.
Alright, a little bit of an echo there. Alright, so while stack, we're going to loop through and we're going to return none if the target value is not found. Otherwise, we're just going to keep looping through. The way we loop through is we're going to append items to the stack. We're going to append items to the stack. Okay, so the first thing we have to do is pop from the stack. So stack, so we're going to take a node is equal to stack dot pop. Node is equal to stack dot pop. And we can check if node dot val is equal to target. Then we're going to return none. Or actually, no. Not none. We're going to return. What do we do? We return. Or first we got to append. So results dot append node dot val. So every time we pop it, we're gonna append the value. What was that? Was that a follow? Ashish, hello. Thank you for the follow. So we append a value, and then what we have to do is we append the value, and then we check though if the target is found. We're just going to stop. So if node dot val is equal to target, then we're going to return the resulting list. And if that's not the case, then we got to keep adding onto the stack, because that's how we move through the tree. And so we want to say if node right then we want to add to the stack node right. And the same thing if node left, want to add to the stack node left. And the reason we're doing right first is because we're doing a depth first search. And so that means once we loop back around, we're going to pop off the left node first, because it's going to be on top.
Steve Josh. Left vs right doesn't matter for DFS.
What was that? Left versus right doesn't matter. I thought it did matter. Or was I thinking, am I thinking breadth first search? I thought breadth first search it didn't matter.
Steve Josh. You should be going directly to the target, right?
I should be going directly to the target. Oh, yeah, that's what it was. That's what it was. I think I was thinking that I have to do a certain order if I'm like using the binary tree, like in terms of order. But yeah, so in terms of just finding a target, then it doesn't matter. Yeah, you're right. I was thinking of that. Anyway, so yeah, either order. And so you are adding them on, and then so later you're gonna pop them off and do that thing. And then
Steve Josh. Maybe you are doing level first traversal.
level first traversal. What does level first traversal mean? Let me look that up. Level first traversal. So yeah, breadth first traversal, right? That's what you were saying. Isn't this depth first though? Because when you do
Steve Josh. Yeah, BFS is by level.
yeah, but so the way, are you saying the way I'm doing it doesn't look like?
Steve Josh. 4 trees.
Are you saying the way I'm doing it right now doesn't look like depth first search? Because I'm pretty sure that this, like, yeah, I think this is depth first search. Or were you saying? I think this is depth first search. Okay, I missed something here. Let's go through. So we have if the root is not null, we append the root. Then we're looping through while the stack is not empty. And we say a certain node, we pop off the stack, the node, and then we say we append the value into the result array. And then we check to see if that value is the target. If it is the target, we return the result. If not, then we're checking to see is the right of the node null. And if it isn't null, then we're gonna append that node to the stack. And if the left of the node isn't null, we're gonna append it to the stack, right? And so let's say it was A, pop off, A's not the target, E's the target.
Steve Josh. With a DFS, you shouldn't need stack to store the next nodes to be processed. You should draw out a full 7-node tree and the order in which the nodes will be visited with your code.
With the DFS, you shouldn't need stack to store the next nodes to be processed. You should draw out a full 7-node tree and the order in which the nodes will be visited in your code. How would you draw out the tree? Without using a stack.
Steve Josh. Well, maybe you need stack since this isn't recursive code. But I think this is BFS now. Teve Josh. Draw on paper, I mean.
Oh, okay. Yeah. Like here, I can show it on paper. So let's look at this. So we're gonna have nodes. And hold on 1 second. A, B, C, D, E, F. A. B. C. D. E. And 1 second. F here. Let's get some lines. And so we're gonna have a stack, or let's do it like this. We're gonna have a stack. I have a stack. And so we're going to place items onto the stack. And so we're also going to have the result array. So we have a stack and we have the result array. So the first thing we put into the stack is A. Right? Put into the stack. So we start out here. We put A onto the stack. And then we pop off A. And when we pop off A, we're putting it into the result. And then we have node right and node, or node right, node left. And we're going to put C here. C and B. C and B. Right? So we'll put C first and then B next. Right? And so when we loop around again.
Teve Josh. Nice diagrams.
Thank you, thank you. So we can say also like this is the current. So in this spot we have the current is A. And we have the stack. And so the next step would be right here. The current is B. And this stack would add on. So you would add B here. and the stack would add on. We would take this off, delete this, and because B has 2 children, he would add on 2, and he would say write first, so or write first E and D. And so after this one now, so you have, let's make it a different color, this one. Once you loop around again, the next one you pop off is D. And so you say the current is D. But that's what makes it depth first search, right? So because I'm like, when I'm stacking it up, I'm going directly downward first, rather than like saying, going this way and then this way. You can't, because you can't do depth first search with a stack. You have to do it with a queue. But yeah, like you would either, depending on which direction or which direction you choose, the left or right first, you either go down the right tree first all the way down, or the left tree.
Josh. You do A, then B, then D. Okay, that is DFS.
Yes. So, but so it's DFS, but now in the code, I did something wrong. In this code, I'm returning the result, but I'm not returning the D here. Or I'm returning an extra D. We're searching for E. Oh, I see. Okay, so
Josh. You don't pop from result. Josh. When you go back up.
So I need to pop from result when I go back up. So how do I do that? So if so what is, it's going to, how do I do that? Let me look at my drawing. So we have depth first search, but now we have this problem if we go all the way down here, but our target's on the right side. Then we're gonna have a longer, so we could pop it. So if we look here, let's make one more. Let's make one more here. And we go to the current is E. But we don't want D here. So how do we get it to be ABE? So we have to pop it at this stage. So before we go into E, we have to pop it. But only that one. Because like before, we're not going to pop B. How do we pop only that one? Because we don't want to pop B before we get to, like, let's say we go down to D, we don't want to pop B. So we're going down to D, we don't want to pop this, but we want to pop this before we go to this. So how do we do that? I was thinking maybe we don't even... No, I don't know. Is this possible?
Teve Josh. Do it recursively, or use path node tuples in the stack instead of just the nodes.
Path node, okay, so yeah, recursively would make sense. And then, so if I don't do it recursively, we would use path node tuples in the stack instead of just the nodes. Path nodes. How would that work though? Path node tuples in the stack. Alright, let's try recursively. Let's take a break on this. Let's try recursively.
Teve Josh. Stack is just what's left to process next. It could be used as a stack or a queue.
Yeah. Try recursive. So the base case is return none if not found. Otherwise, return the path. All right, how do we think of this recursively? If there's one node, we would say, is it the target? So we say is root equal the target. then return an array with a root. No. So if there was one node, you would just check to see if they were equal, right? And if they're equal, then you return an array with that value. Now, if there's two nodes, is the first one equal? And if not, then you would travel to the next node. If root dot left let me say so let's say we have ABC and we want to find C.
Steve Josh. Yeah, that should get you one possible path.
That should get one possible path. And what do we do with that?
Steve Josh. Do the right, too. And check which one has the path.
We need to check which one has the path. All right, let's do this. Left path.
Steve Josh. Which recursive call? Steve Josh. S value has the path.
Which recursive call has the path? So you're saying return the one that has the path. So let's say we have the left path. Or let's say we have this at the bottom right here, and we're searching for F, and we go down the right path. And no. We go down the right path. And we're checking to see, okay, is the value equal to the target? And if it's not equal to the target, then we have to keep searching. Right? So let's say we go down again and we go down to the F. Now it's equal to the target. Or how do we return? Okay, so how do we append the C though?
Steve Josh. X dot append, Y, or X dot append, 0, Y.
X dot append Y, X dot append 0, Y. Do I like have some sort of result array or something? God, I just can't right now. I'm gonna look at this real quick.
Hey programmers, welcome back. Right now I want to go over the approach for this tree pathfinder problem. So this is going to be a pretty interesting problem. So basically what we want to do is, given a binary tree, we want to basically find a target. But this time around, instead of just returning a simple boolean, if we are able to find the target within the tree, we want to return the path to that target, right? And so what we want to do is return an array representing the path to that target from the root. In other words, you can definitely find BE within the tree, and we want to return an array containing ABE, right? Starting at the root, what are all of the nodes we'll have to travel to get to the target? So let's say in another example, our target was C. C is definitely found within the tree, and the path we should return is just this path, right, of AC. Cool. A final scenario we should probably think about is, what if we had a target that was not found? In other words, what if our target was a letter like P? P is nowhere to be found in the nodes of this tree, so in that scenario, we just want to return null, right? So that'll be an edge case that we have to handle. All right, so looking at this problem, it may seem like a tough one, but hopefully you're able to recognize some patterns that we've seen before, right? So a previous problem that I'm reminded of here would be the tree includes problem. We just have to return Boolean, right? True or false is the target within the tree. This time we just want to return more information, right? That is, if it's found, I return an array representing the path to where I can find it. But if it's not found, instead of returning false, I return null here. right? So hopefully you're doing these problems in order. If you haven't done that tree includes problem yet, I recommend you do that one first. But how can I start attacking this one? Since in this problem, they want us to basically return a path, typically I find the depth first recursive code the best way to solve it. And so I'll go ahead and trace through how that can work in this approach video. And so we'll stay committed to solving this one recursively with a depth first. And let's say we were stepping through it as if we were looking for a target of E, right? So what I want to do is, of course, begin with my base case. And the most important thing I need to establish in my base case is a consistent type, right? So I know in general, right, this problem asks us to return an array of some values. So even my base case should return an array of some values, right? It probably will just be a small array. And so let's say we had a scenario where we were at a node that contains our target. In other words, we have a match, right? If I have a match, that is, if I run into a node whose value is E, then I think that node can immediately return an array containing the value E, right? And that would just be consistent with the shape of the problem. So I'm just going to plug in this visually right where I find the E node, right? So I'm saying that, all right, when I make a recursive call on that E node, I should treat that as a base case and just automatically return an array filled with the value or character E. Nice. And now we're going to need another scenario, right? That matching base case kind of sounds like the affirmative, meaning we did find the thing we're looking for. But what about the opposite scenario? What if we don't find what we're looking for? Well, we know we basically hit a dead end in our tree, and there are going to be many dead ends, but we hit a dead end in the tree whenever we call upon a null node, right? And we've seen this pattern a few times before, right? So just visually, although it's not going to be something special we have to account for, but at least in our drawing, I'm going to explicitly draw what our null pointers would be. And they would look like this, right? Notice that I'm not going to actually draw any like null pointers from the E node because I just said that it's its own base case, right? And it's going to return an array of E. Cool. So for all of these null nodes, they should return null, right? And what's the logic behind that? Well, I think about all of my base cases as if they're their own problems, right? So typically a null node, if you kind of interpret it as its own tree, a null node is the empty tree. And I know that the empty tree should always return null because you can't possibly find any target within the empty tree. And that's consistent with the problem. Cool. So now that we have some base cases laid out, how can we use these values to build up higher level solutions? So let's say we look at this D node, right? We're going to evaluate this depth first style. And what should this D node return? Well, if it looks at its values that it's receiving from its left and right, it's getting null, right? So if I get a null from my left, that means, all right, I did not find my target in the left subtree because my target's E, right? In the same way, if I get a null on the right, that means I did not find my target in the right subtree. So if I don't find my target in either of my subtrees, and I don't contain it at all myself, right, because D is not equal to E, then this node can return null, meaning we cannot find a target at all within this subtree. Things get more interesting when we evaluate this B node, right? It's ready to compute. So if I root myself at this B node, right, so I have the perspective from the B node, on my left, I'm getting null, which means I didn't find anything in my left subtree, but along the right-hand side, I'm getting back an E, right, an array of E, which must mean that I found the E in my right subtree. And so what I'll do is I'm going to just drop the null on the left, and I'm going to prefer to just analyze the right value, right? And so I know that I need to incorporate this array of E into my final answer, but I need to add myself, right? Because I have to construct and return the full path. So I'm going to put the B value at the front of that array, right? And if I pause for a moment here, this seems logical because if I root myself at the B node, above it I have the return value of an array of B comma E, and that represents the path I can take from this subtree to the E node. Cool. We'll evaluate the rest of this. So at this F node over here, I have two nulls, which means I didn't find my target in either scenario. So this should just return null. And at the C node, same thing, null on left, null on right, so I didn't find anything, so this should also return null. And finally, at my top level root, I look at these two values, right? If I'm rooted at A, I have an array of BE on my left, which means I found something, but on my right, I have null, which means I didn't find something on my right, so I prefer the left-hand side here, right? But what I need to be sure to do is put my own value, because I'm the parent, into this path, adding it in the front, so ending up with ABE. And it's important that we get the correct order of things here. And logically, this return value of ABE is our top-level answer, and it represents, of course, this path within the tree. Cool, so that seems pretty reasonable to code up, right? Something to watch out for when I code this one up is probably the fact that I'll need two base cases, right? I need to catch a scenario where I have a match, and I need to also catch a scenario where we have a null node and return null. Cool. That being said, what can we say about the complexity of this algorithm? Well, like always, we'll say n is a number of nodes, and I think if we do this the correct way, we should end up with a time complexity of O of n, right? Because we should just have n recursive calls, right? A call for every node within the tree. However, if we kind of don't do efficient operations, I can kind of imagine if we built the return array in a very inefficient way, we might end up with a larger time complexity. So what I'm arguing for right here is if we do this in the most efficient way possible, so this is kind of like a code detail, we should end up with an O of n runtime. Space complexity should also be O of n for the stack space, and I guess also the return value. So again, something that we'll have to stay super focused on is try to avoid slow and costly array construction, right? In other words, instead of creating and copying over a new array as I build up my solution up the tree, it would be better if I can keep a running array. Don't worry if that means nothing to you right now. You'll realize this when we code it up together in the walkthrough video. So I'll catch you there.
I don't understand that last part. But I think what do we do if it's none? Like if it's none, because I was thinking like after this you can like maybe return left path. So if you find it, you return a
Return in array contain return a path. Typically, right, that matching base case kind of sounds like the affirmative, meaning we did find the thing we're looking for. But what about the opposite scenario? What if we don't find what we're looking for? Well, we know we basically hit a dead end in our.
So we're gonna have root.val plus, why can't I, what? Val plus left. Like I'm thinking something like this. If root doesn't exist, we should return null. Like if not root, return none. If not root, return none. If root.val is equal to the target, then return root.val in an array. And then we go down the left path and the right path. Now, what do we do if they're equal to none? If not left path, then left path equal to empty array. Something like this. Left path reached before assignment. Because sometimes it doesn't go in here. Maybe we do that in here. Oh yeah. How do I do this? Well, I don't need this. Because I already checked if it's not null, right? No. I do need it. If not root, return none. Wait, do I need this?
Steve Josh. I guess that works.
Expect A, B, E, and actuals A, B, D, E, E, C, F. I'm just adding all of it.
Steve Josh. Left and right doesn't make much sense.
Left and right doesn't make much sense. Yeah, because you're not... Yeah.
Right, so hopefully
Steve
we had a
Josh.
scenario. Well, we know we
But this looks very close.
The logic behind that. Well, I
It's
think about all
close.
of my base cases as if style. And what should this D node return? Well, if it looks at its values that it's receiving from its left and right, it's getting null, right? So if I get a null from my left, that means, all right, I did not find my target in the left subtree, because my target's E, right? In the same way, if I get a null on the right, that means I did not find my target in the right subtree. So if I don't find my target in either of my subtrees, and I don't contain it at all myself, right, because D is not equal to E, then this node can return null, meaning we cannot.
So if both return... I don't
Not
know how
find
to
a
do
target
this.
at all within the subtree. I need to add my...
I'm just going to look at this. I don't know.
Hey, programmers, Alvin here. Right now, I want to go over a Python solution for this tree pathfinder problem. So hopefully you already watched the approach video. If not, highly recommend you do. And I'm going to jump right into the code. So to me, the most reasonable way to solve this one is to do it recursively. And typically, I'd say that's a rule of thumb for all of your tree problems that deal with pathfinding, but don't quote me on that, right? And so we'll start with our base cases. So I'm going to need a base case for when I actually find my target. So if root val is equal to the target, then what should I return? Well, I need to return a path, and the path is represented by a Python list containing all the values that I can take to get to that target. So if my root val is equal to my target, well, then just return a list containing that value. I guess you could have also thrown in target because they're definitely the same. Nice. And what also feels good about this if statement is I can think about my base case as also if it's its own input. And so imagine I just gave you a tree with just a single node. If your target was that one node, then the path would just be an array containing or a list containing that single target. Cool. And then beyond that, and I'm going to do this recursively, so I'm going to need to make some calls, right? So pathfinder root left on target, same thing for root right. Something that you should start to feel comfortable doing is you may not know like the big picture of like what your final code is going to look like, but you are definitely aware of what patterns must show up, right? So I'm going to need to definitely call recursively on my left and right. And then from there, we're like, all right, it looks like my target doesn't need to change, right? I always look for the same target. Now think about what these calls return, right? I either get back null if I can't find the target in the left subtree, or if I can find it, then I get back a list representing the path to the target. Cool. And so based on what these calls return, I'll go ahead and check it. So maybe I'll call this my left path, like this, left path, and right path respectively. And bear in mind that these variables of left path and right path, they are either lists or null. And I need to actually verify whether they're null or not, right? So I'll check over here maybe if my left path, and by null I mean none, I guess, right? So if my left path is not none, then it's a list, right? So if this if statement is true, that means I found my target in my left subtree, right? And so what do I want to return? Well, I want to return a list that represents the path to that target. And so I know I have a partial path in left path. I need to just put myself, so put root.val at the front of that path, right? So you've seen me use this syntax before. I can create a new list literal, spread out or splat the elements of that current list, left path, and just put myself at the front of it, root.val, just like this. Cool. So this is just creating a...
So if left path, then we want to return a list with root.val and spreading a previous list left path. And we do the same thing for the right. And now at the end, you would probably, is that it?
A new list, taking all the original elements of my left path and then putting root val at the front. And I just write symmetric code for my right path. So we'll call this guy our right path. And bear in mind that in the problem, they actually tell us that the tree contains unique values. So that means a value only appears once in the tree. So I'd only find my target in either my left path or my right path, but not both, right? Because in just one of my subtrees. But it could be the case that it's neither. So sometimes we want to return none if we just can't find the target at all, in which case we should handle that over here. So if we make it past these two if statements and we don't return either, then by definition, we cannot find our target at all in this subtree. So I'll just return none. Cool, so this code's looking pretty good. There's one thing we should be aware of in terms of the complexity I did mention in the approach video, but let's go ahead and run it and see what we get. So we'll run it through some test cases. So it's going to be an error. It says none type object has no attribute val. Pretty common bug when it comes to writing your tree algorithms. And it's probably the case where root is none, right? Because there are definitely some trees. For example, if I look at this tree, let's say root is the C node. If root is the C node, I don't hit any base case, right? And so when I calculate my left path, I'm calling pathfinder of root.left. If root is C, then root.left is none because C has no left. And that would throw an error, right? Because if I'm making a call and root is none now, I say none.val. And that explodes and gives me an error exactly on line 8. Cool. So like all of our tree algorithms, typically, especially if it's recursive, we need to handle the case. All right, before you even do any of this logic, it could be the case that your root is actually none. And in which case, you could just return none. In this problem, like returning none represents the fact that we did not find the target or we cannot find the target in this subtree, right? So if you have an empty tree, right, none represents an empty tree. If you have an empty tree, then you definitely can't find the target. So just return none. So that should be a nice fix. Give that a test now. Cool, we're passing most of our test cases, and it looks like we did pass all of them, but you may notice for this last example, we have a pretty large elapsed time. Definitely something spiked over here. And so we'll take a look at what test 06 is. It's a very large tree, right? So looking at this little stub they have here, looks like they just programmatically create a massive tree. This tree only has right pointers, so it just goes 0, 1, 2, 3, all the way to like over 19,000 nodes, so it's really big. And then from there, they're looking for, looks like value 16281, which would be somewhere within this chain, this tree, because they're just counting by ones, right? And so we should be able to return that path. What's obvious for this large input, our code is kind of slow, right? One thing I mentioned in the approach video was to be aware of any list operations you do. And in particular, I can identify these lines as a culprit, right? So basically, if I look at this line and I just isolate it, I'll think about what's the runtime of that line, right? So I know that doing this syntax, right, splat left path, that takes an existing list and it basically unpacks all of its inner items, right? So let's say that my left path was of size n, this entire expression would run in O of n time, right? And that's this line itself. Now I think about all of the calls I make. I'm going to have n calls, and any particular call basically iterates n times. I'm looking at n squared as my runtime. Cool. So this is a common constraint or common issue you might have for your problems that recurse and also return lists as output. And so I'll show you a fix for this. So instead of creating a new list every time, right, this copies over a list and creates a new one. If you want to have like the fastest possible runtime, although it will probably add some just like complicated pieces of code, you will have to just basically insert your elements into a single list over time, right? So don't create copies of lists. And so what I'll do to fix it here is maybe I'll just go ahead and I'll mutate my existing path. So if my left path is none, then I'll say, all right, left path append and add to it root.val. And then I should just be able to return left path, because now I definitely put root val on the inside. One thing you might notice is technically append will add your root val to the end of the list, so the right-hand side, which means that I'll end up with things backwards. And so I'll need to come up with another fix for that. But at least append.
So you would just append it.
End runs in O of 1 time, right? If I inserted at the front of a Python list, that would also take up inefficient O of n time, because inserting at the front of a list would have to shift all of my indices over, right? If I insert at the front, then index 0 has to move to index 1 to index 2, index 2 to 3, and so on. And so we'll just have a fix like this for now, and then we'll course correct once again. Something that you should start to get comfortable with is, have many renditions and iterations of your code, right? Just change it over time. So I like to make small changes and then keep on course correcting. So I'll give this a shot. Probably will get some reverse output, right? Yeah, so we expect ABE, we gave back EBA again because we're inserting or adding our root val at the end of the list. But I'm pretty confident that now I'm not copying over many lists, so at least this will run, it seems, in O of n time overall, right? The entire recursion. And so what I would do to fix this is just make a main function that reverses the final output. And let's say you're doing this on like a coding challenge platform or an interview. I think it's really important that you don't change the function signature that they're going to test. So in this problem, like our specs are going to test a function called pathfinder. So maybe I'll rename the old recursive function like underscore pathfinder. Pretty common notation in Python. Typically, if you for those of you that don't know, if you name a function with an underscore just as like a style point, it kind of indicates to other people reading your code that, hey, you shouldn't really invoke this function top level. It's like a helper function. And so my main function will be the regular pathfinder. So all I need to do is go ahead and call my underscore pathfinder function. And I know it's going to return some results. So I'll call pathfinder, pass along the same root and target. And I need to verify whether result is none, because if it's none, then I should not reverse it, because that would break my code. But if it's a list, I should reverse it, right? So if result is none, then we shall return, I guess the result, which is, I guess, none. Maybe I'll just write it like this, it's more obvious. But otherwise, if result is not none, then it must be a list, in which case I can reverse it. So I can return. Python reverse syntax is pretty slick. I'll just say the name of the list. And
if result, then what is this?
Maybe you're familiar with like the slice syntax, right? So typically you can give like a start and end for like a range you want within your list. You can also give a third argument representing how you want to step. If I step by -1, that would reverse it. And I want to basically have the entire list and only reverse it, right? So I'll just say blank blank and then -1. Cool, so that's just reverse the list. Technically, this syntax creates a new list that is reversed, but that's okay because I'm just doing this reversal step once at the end, right? I'm not doing it within the recursion. So that code looks pretty good. So I'll give this a shot now. We'll run all the test cases, see what we get. Nice, and we have a much better elapsed time for that test 06. This code would be an O of n time, right? So for this recursive step by itself, the entire recursion, because I make n calls, and any single call is just O of 1 because append is basically free now. This entire recursion is O of n. And then when I do the reversal at the very end, that's also O of n, but they're not nested, so I don't multiply them. So I'm basically looking at, in terms of time complexity, O n plus n, right? Which simplifies to just a single O of n. Cool. So there we have it. Do bear in mind for the future, this little optimization that we made, right? Typically, when we're kind of creating many lists by copying them over, you're going to incur like some runtime penalty. So maybe figure out a way where you can just add to an existing list. That being said, whenever I'm doing some new problems out in the wild, what I'll typically do is focus my initial energy on just creating a working solution. So maybe it's a slow one. And then I'll analyze my code according to Big O. I'll take note of any expressions or pieces of code that are inefficient, and then I'll make changes to those expressions. Right? I like to work on my code.
You gotta have that process of doing it that way too. Get too caught up in trying to get the final answer. So what we learned is, let's go through this code. We gotta check first if the root is not null. And if it's not null, or if it is null, then we return null. If it's not null, then we check to see if it's the target. And this would be a base case, and we just return that target value if it is the target. Otherwise, we're going to traverse down each path, and for the left path, we put in the left root and the target, and we check to see if it's not null, then we're going to append that value to the left path. And we're going to return the whole appended list. And this is better than the spread operator because the spread operator is an n, or is a linear type of operation. And so by appending it, we make it O of 1 time. However, it's going to end up being backwards, so we're going to have to reverse it later. We do the same thing for the right side, and we return none if no target was found. And then once we get out into the main function, we just reverse the list, which takes O of n time, but it's not inside this loop, so it's not O of n squared. And so that's the problem. So I gotta remember that we're going down left and right path. And what we did here was store the result into a variable that represents an array. It's going to be an array. And so it's pretty interesting in Python. I guess what made it an array was appending something. And all of a sudden it's an array. Okay. I wanted to see, hold on. So the pen, append and not append, okay. Write a function tree value count that takes in the root of a binary tree and the target value. The function should return the number of times that the target occurs in the tree. And so we have here six occurs 3 times. So we have to traverse through the whole tree and count how many times a current number or a target number appears. Let's do the same depth first search, right? So recursive depth first search. This time's gonna be a little bit easier. But let's check to see if not root. So if root is null, we're going to return 0. Because we're returning integers now. And if root.val is equal to target, we're going to return 1. One represents that it's there. And now we have to traverse down the left and the right to check. And so we can say left count is equal to tree value count root left target left count and then right count and then we want to add them together. And that's how you get the total. Maybe you have to do this. No. Left count is referenced before assignment. Is this it? Okay, so now just something's wrong. So we go down the left side. We're checking to see if like if we start with 12 and we just check to see, okay, is 12 the target? It's not the root, or I mean, it is a value or a node. It's not the target. So we go down the left side. And we have a target. So we return 1. But we don't want to return. If it's the target, we don't want to return, do we? Because we want to keep going down the path and checking. We do like can we do if root value is equal to target, then we're going to add 1. Like, can we set count is equal to 0? Count is equal to 1. No. What am I doing? I was trying to say that if the target is reached, we want to add 1. But we want to keep going. If target is reached, we add 1, and we keep going down the tree. Target is not reached. So the count remains the same. Once we get to the bottom, we check to see once we get to the bottom here, we see, okay, is it this returns 0 and 0, and then we add it up. This returns 1. And 0. And then we add it up. Yeah. maybe I do it here. Count is equal to 0. Count plus left count plus right count. Left count is equal to the sum of all things on the left. Same with the right. There we go. So if it's null, return 0. If the target is found, we can set this to 1. Otherwise, you're going down the left tree and you're adding them up, and you're going down the right tree and you're adding them up. And you're adding the 1 of the current instance to the left and the right, if the target value is found. And going through the whole tree.
Hey programmers, welcome back. Right now I want to go over the approach for this tree value count problem. So in this problem, it's pretty straightforward. We want to take in a binary tree containing some values, and we're also going to take in some target value. What we want to do is return the number of times that that target appears in the tree, right? So if our target is 6 given this tree, the answer you should return is, of course, 3. There are a couple ways you can go about solving this one. I think no matter how you solve this problem, you're probably going to end up with either a breadth first or a depth first solution, right? So you're probably by now understanding how to use the breadth first and depth first traversal, right? If you do it iteratively, all you need to do is just write your core algorithm to iterate and touch every node within the binary tree. And then whenever you see your target, after you check it, you just increment some counter. And by the end of your function, you return the counter. So in the walkthrough video that's coming up, I promise that we'll implement both the iterative and recursive version. Just for the sake of this illustration, the iterative version is pretty boring. So I'm going to prefer to step through, like I always do, the recursive version, because I feel it's especially elegant, right? So for this recursive code that we're going to commit to, how do I go about solving it? Well, always start with your base case. You're going to have a type of base case, or at least some logic, maybe I should say, where if you find a matching value, then you need to increment some count, right? So essentially, whenever I see a node whose value is 6 within my tree, then I'm going to do like a +1 somewhere, somehow. And for my other base cases, typically, we always write a base case about the null nodes within our tree. For a null node, I should basically return 0, right? And what does that logically represent? Well, I always, in my brain, try to consider null nodes in any base cases as if they're their own top-level input. So if someone gave me a null node, that means they're giving me the empty tree, right? And they ask me, all right, given this empty tree, how many times does a target of 6 appear? I know without a doubt the answer is 0, right? A target can't appear any times within an empty tree. And so I'm just going to plug in those values here. So I can already kind of foresee where nodes of this tree have their nulls to the left and right. They would kind of all appear here. And I'm saying that those calls upon the null pointers would return 0. So notice if I look at the 6 node, that's the farthest right as possible. It has a right child of 12, but it has a left child of like null. So what I'm saying is that left child is going to return 0. Right? By now you should be familiar with this pattern, especially if you're doing these problems in order, which I highly recommend. All right, so let's root ourselves at this 4 node, and how can we recompute our solution here, right? I want to build up these small values into our larger top-level answer. And so what I have to do is just some arithmetic, right? So I know that I have 0 count to my left and 0 count to my right, and my current node contains a 4, and 4 is not 6, right? I'm looking for a 6. And so overall, I can just add up these two zeros, and I leave it at 0, right? So basically I'm saying within this small subtree rooted in 4, I find my target 0 times, which makes some sense. Things get more interesting when I evaluate this node over here, right? So I have a 0 on my left and right, and that means the count, or the number of occurrences, within my left and right subtree, respectively, right? But then I also have to consider my current node's value as well. My current node is exactly 6, so I actually need to count that, right? So I do 0 plus 0 plus 1, because I'm counting myself, and this node should return 1. Now we'll evaluate this node over here, and I need to, again, combine and add up these different counts, right? So basically, if I root myself at the 6th node, so I'm from the perspective of the 6th node, I found 0 occurrences in my left subtree, I found 1 occurrence in my right subtree, and I myself am 1 occurrence. So I do 0 plus 1 plus another 1 for myself, that gives me 2 as a return here. And if I take a quick look at what I'm really saying, I should have a correct count of 2 because of these 2 nodes, right? I'm able to check for correctness even as I build up these sub-solutions. Awesome. Now, nothing fancy. We'll evaluate this 12 over here. I know that this 12 node is going to return an ultimate 0. Now, bubbling up a little bit at the 6 node, this 6 node is just going to count itself, and it has 0 on its left, 0 on its right, so this one returns 1. Now, finally, at the ultimate root, right, I do the same check. I have 2 counts on my left, I have 1 count on my right, and I myself am 12, so I don't count myself. So I just do 2 plus 1, giving me a final answer of 3, which is exactly what we expected. Cool. When it comes to the complexity of this, it's actually really simple. Like we always say, n is the number of nodes for this tree problem. Time complexity is just O of n due to the number of recursive calls. We're going to make a single call upon every node of this tree. And if I think about the logic we need on the inside of any particular call, it's just going to be some addition, right? I'm just adding a few different numbers, and it's not a dynamic amount of numbers. So I estimate that a single call will run in O of 1 constant time, but because I have n calls, overall, my complexity seems to be O of n for the time. Space complexity also seems to be O of n, just from our stack space, just like usual. All right, so that seems pretty straightforward to code up. We'll watch out for a few different pieces of logic, right? We need a base case, where if our node is null, we're going to return the value 0. And then whenever we have a matching node, that is a node whose value is the same as my target, I need to somehow do some addition of 1. I need to count it. Cool, so hey programmers, Alvin here. Right now I want to go over a Python solution for this tree value count problem. So we'll jump right in. I think this time around we'll start off with the recursive solution. So we know that this problem has us do a count, which means we need to do some addition, right? And we'll start with our base case. One of our base cases is going to be if our root is none, right? So if root is none, I can treat that as if it's its own top level input. So that kind of means the empty tree, right? So how many times could I find the target in the empty tree? Well, that's definitely 0 times. So return 0. Cool. Now we're going to need our recursive calls. And I know that I need to call the function, right? I'm going to pass in root to left and look for the same target. And the same thing for the right-hand side. And what do these calls return? Well, they're going to return to me numbers, and the number represents how many times I can find the target in the left subtree, and also how many times I can find the target in the right subtree. So what I want to do is take the total of those counts. So I'll just add them up, just like this. Cool. And then I need to consider myself. So I need to consider root.val. Notice I haven't accessed root.val yet. And so depending if root.val matches my target, I want to add 1 or not, right? So maybe I'll just use a variable here. I'll say match, and I'll use some Python ternary. So what I can check is, all right, I'll use 1. I'll make match 1 if the root.val is equal to the target. Otherwise, I'll make it 0. So this is what a Python ternary looks like, if you're unfamiliar. So when the value is equal to the target, matches 1. When the value is not equal to the target, matches 0. And then I can just actually add that value for match into my running total. Right? Then from there,
So doing it this way, match 1 if root dot val is equal to target, else 0. And then instead of doing this, we do probably something like this. Match plus equal to this, and then return match.
I'll just return that final value. Cool, so pretty short code. Let's go ahead and test this for Python. Cool, and there we have our recursive solution for tree value counts. While we're here, I'll also, of course, show you maybe
Use a bathroom.
an iterative solution. Maybe I'll choose to do the breadth first iterative. So define tree value counts once again, taking the root and the target. And I do believe that in this problem, we could be given an empty tree up top. So does that exist? Yes, it does, right? So sometimes I give it in front of my queue so that whenever something leaves the queue, I'll check. All right, one iterative solution you can come up with. I'll give that. We saw a recursive and also iterative solution for this. Technically, we implemented this as a breadth first. I'll leave the depth first iterative version to you.
All right, I'm gonna take a break.